When you are doing Lewis structures of polyatomic ions, it's pretty much the same as Lewis structures of neutral molecules, except that you have to take the charge into account when adding up the number of electrons. So nitrogen has 5 valence, hydrogen has 1 valence, and there's hydrogen has 1 valence, and there's 4 hydrogens, so that's 9. But then I got to take that plus 1 into account. This ammonium got the plus 1 charge by losing an electron. So that's why I'm going to do minus 1. And I'm going to use 8 total electrons in this molecule. So nitrogen's my central atom. 4 hydrogens are on the sides. 1, 2, 3, 4, 5, 6, 7, 8. I've used 8 electrons. I gotta check if things are satisfied. Hydrogens all look good. Nitrogen looks good. So yes, everything is satisfied. The last thing you have to do to indicate that it's a polyatomic ion is you have to put it in brackets with the charge on the outside. Now, ammonium's not an example of this, but there are things that the same formula exists for a polyatomic ion and a neutral compound, something like sulfur trioxide, SO3. So SO3 has one particular Lewis structure, and then if it's the sulfite ion, if it has that -2 charge, it's a different Lewis structure. And so to indicate which one you have, any polyatomic ion you put in brackets with the charge on the outside. Carbonate, carbon has 4, oxygen has 6 times 3, so that's 18 plus 4. And then the -2 charge it got because it gained the entire molecule, not one in particular thing, but the entire molecule gained 2 electrons, so that's a total of 24. So this plus 2 comes from the fact that it has a -2 charge overall. Carbon's my central atom. Single bond to each of the oxygens. So that's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, 24. I have to check if things are satisfied. All the oxygens are satisfied. They all have 8. But the carbon, look at the carbon, it only has 6. So when I'm in that situation, remember you erase a lone pair, make it a bonding pair. Well, the question becomes, which lone pair do I erase? Do I take it off of this oxygen and make the bonding pair there? Because that would satisfy the carbon. Do I do it with the bottom oxygen and put it there? Because that would satisfy the carbon. Or do I do it with the one on the right? The answer is it doesn't matter, actually. It doesn't matter. This is something called resonance, which I will get into in just a moment. But that double bond can be between carbon and any of the oxygens. So when you're doing this Lewis structure, it doesn't matter which one you put it with. What matters is that it's double bonded to one of the oxygens and it's single bonded to the other. Oops, I never put those back when I took them away. It's single bonded to the other 2 oxygens. So again, throw that in brackets with the charge on the outside. At this point, for clarity's sake, if you did want to start representing bonds as lines, you are welcome to do so. Lone pairs still need to be dots, but you can take a bonding pair, so 2 electrons, and represent it as a line because it just makes everything a little bit neater. If you like the dots, stick with the dots, but you can do the lines too. So I said this is something called resonance. A molecule shows resonance when there is more than one Lewis structure that can be drawn for that molecule. So O3, which is ozone, will have resonance. O3 is 18 electrons, and it's just 3 oxygens in a row. Start with single bonds. So that's 4, 6, 8, 10, 12, 14, 16, 18. So each of the oxygens on the end has a satisfied octet. The one in the middle doesn't. So I need to erase a lone pair. Getting ahead of myself. I need to erase a lone pair and make it a bonding pair. It doesn't matter which oxygen I do it from. So the way you actually show this, that this has resonance, one erase, goodness, is you draw both with an arrow in between. So that's one. And then being double bonded to the second oxygen is the other. And that's saying they're both valid structures. What actually happens, double bonds, single bonds, triple bonds, they all have a particular length. And it turns out when a molecule has resonance, like ozone, the bonds are, instead of being the length of a single bond or a double bond, they're about a bound and a half. So really what that means is that bond, that second bonding pair, kind of floats between the two sides. So nitrate is also going to show resonance. This has 5. Oxygen has 6 times 3. And then because of the negative charge, I'm going to add one more. So that's 24. Nitrogen's my central atom. Let me write this smaller because I'm going to have to draw 3. So nitrogen's my central atom. O. Start with single bonds. Put the rest on the outside. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Nitrogen's not satisfied. So erase a lone pair. Make it a bonding pair. So that's one valid structure. Having the double bond on the other side is another valid structure. So that's another one. Make sure I did that right. And then, I'm missing 2 here. That's why. I just made that arrow too big. There we go. And then a third valid structure would be having the double bond on the bottom. So all 3 of those are valid Lewis structures. It is a polyatomic ion as well, so I guess I should put it in brackets with the charge on the outside. You don't have to draw all 3 or the multiple resonance structures beyond today, but I do want you to do it today just to get some of that practice in.